I'm gonna talk today about hardware wallets for cryptocurrencies, and just a disclaimer, I'm not gonna raise any FUD about current wallets being insecure or something else. I'm just suggesting an alternative way of making them more secure by design, by changing by applying different architecture that should in theory be more resilient to attacks that we already saw that could happen. So what is a hardware wallet? On Bitcoin Wiki, there is a small definition that says that they are devices that are kind of more secure for storing cryptocurrencies than ordinary software wallets that are, in case your computer is exploited or hacked, people can take your funds. So this is supposed to be a mean of storing cryptocurrencies in an isolated way to that should make remote attacks impossible. But in practice, that wasn't the case, because we saw some examples of possible attacks on hardware wallets that are really widely deployed, like Trezor, for example. Its architecture is pretty simple, so they use basic microcontroller that is just off the shelf, and they communicate via USB, and they have a small display where they show the transaction that you have to confirm. So what is the problem with this? The problem is that usually these USB stacks are huge, and they are not written to be for secure devices. So it's quite possible that some of these open source USB stacks for microcontrollers contain some bugs that can be exploited, and it can allow people to steal funds from these wallets remotely. So what happens is, instead of having an isolated device, someone can actually abuse that device to either write into the protected part of the memory, to rewrite parts of the memory, or even escalate to arbitrary code execution in some of the older firmware versions of Trezor. And they have really nice write-up on their blog about these bugs that they had. So that crosses one of one of the properties of these hardware wallets, and that is that they can be used securely and interactively, because private keys do touch potentially vulnerable software. So in case of Ledger, it was supposed to be a bit more secure, because but it's not open source. So that's one of the things that we must also take into consideration when we choose our devices, because in case the code is not open, there is virtually no way for us to validate the operation of that microcontroller. We cannot validate what it's doing when it's signing our transactions. So the architecture of Ledger is like, there is a main microcontroller that talks to the OLED and talks via USB to the PC, and it also has a secure microcontroller that is supposed to be really it's supposed to be much more secure than the average off-the-shelf microcontroller. It's hard to get this one for testing. We cannot easily order a board with this microcontroller online, because you need to sign an NDA with the manufacturer first. And what is the problem? So in case the same we have the same problem as with Trezor, I'm not aware of any of the attacks on Ledger that were done in this way. But let's say hypothetically there is a bug in the USB stack, then we cannot guarantee what we see on the OLED is the transaction that is being sent to the secure microcontroller. So that way. Also, there is another problem, because they actually verify the firmware that is running on this insecure microcontroller by sending it to the secure microcontroller for verification. So this is not really a good idea, because there is a really nice also blog post, like how to actually abuse this mechanism, how to reuse pieces of chunks of code that already exist in bootloader, and then use that space in the firmware to actually just map that, just jump to these functions once they are needed, and once you have to send that data to the microcontroller that is verifying that. So it verifies, it says like, yeah, this firmware looks fine, but on the other hand, that firmware does something malicious. So to sum it up, these wallets like Trezor and its clone KeepKey, they use insecure microcontroller that doesn't have, I mean, insecure, I would say microcontroller that is not meant to be used for secure devices, and it doesn't contain any hardware acceleration for any of the operations that we need for signing Bitcoin transactions, such as SHA-256 or true random number generator, or the elliptic. It doesn't support operations on the elliptic curve that is needed that is required for signing that is used in Bitcoin. But it's open source. It's completely open source. The microcontroller doesn't require any NDA. So Ledger, on the other hand, it's secure microcontroller. Definitely has true random number generator. Definitely contains the accelerate hardware acceleration for SECP256 K1 elliptic curve, but it cannot be fully open source because this part is under an NDA, and we cannot see what's happening there. There is also another way of designing these wallets, like with secure element and like this cold card, for example. But unfortunately, the secure element, even though it is called ATECC, it supports elliptic curve operations, but not for the elliptic curve that we would need for successfully signing Bitcoin transactions. But it can be fully open sourced. And finally, the design that I would propose would be to move the OLED to another microcontroller that is going to be more secure, well, trying to find the most secure microcontroller that doesn't require an NDA, and then putting one communication microcontroller that will do all the heavy lifting towards computers or your phone, or for example, depending on which communication channel it is used later on to the left. So, and I found two microcontrollers, actually one family of microcontrollers, these K82 and KL82. So the difference is that KL82 is just Cortex M0 and K82 is Cortex M4, so it's like price and performance difference. But apart from that, they support all of these. They have acceleration unit that supports all of these operations that we would need for successfully signing Bitcoin transactions. And thus it can be fully open source because it doesn't require an NDA. Library dependencies in major wallets. Well, at least Trezor and Ledger, they don't share any code base, as far as I know. So I checked their repositories and they couldn't find any overlapping in there, even though they are based on the same hardware, similar hardware platform, so same microcontroller family. But they also rent a lot of code from third parties, so not written by the code that is not written by manufacturers, which of course makes sense for some cryptography operations because there is a rule that says like you should never roll your own crypto. And KeepKey, as a kind of clone of Trezor, just relies on the majority of code for it, and it has its own bootloader and firmware. And Cold Card, it uses MicroPython, and we'll see later why it's so why is it bad when it comes to code analysis. And but at least all these three devices to the left are completely open source, and we are able to actually see what's running under the hood. So now I know you might think I'm making my own hardware wallet and I'm rolling my own crypto. So I'm well. Since I'm using hardware acceleration for all of it, I would like to say that I'm kind of interfacing just with these hardware peripherals. So I'm not implementing all the hard operations. I'm just interfacing with peripherals inside the microcontroller. So if there is something wrong with the hardware implementation of these operations, there is nothing I can do. But at least I tried. So comparing the code size, I was just going through these repositories and just getting all the sub-modules that they depend on and trying to see on how many lines of code they depend and how hard would it be to actually analyze the code for vulnerabilities. So Cold Card, as I said, it uses MicroPython, so it's like 2.5 million lines of code. It's almost impossible to manually analyze. on the other hand, Ledger has over 340,000 lines of code that's just the open source part. And Trezor and Keep Key, they have around the same, like 160, 122. Okay, and my implementation was squeezed only into 4,000 lines of code because I had one summer to, this was my like summer project, and I didn't want to invest much time into writing this code. I just wanted to make a proof of concept, to make it, to prove it that the architecture, these wallets can be made simpler and in theory more secure than they are at the moment. On the other hand, it's a bit of an unfair comparison because I used I only implemented Bitcoin wallet, whereas these other wallets implement also other cryptocurrencies. But even if you multiply it with the number of cryptocurrencies that are offered by other wallets, it's still hardly going to reach the lines of code that are present in others. So and out of these lines of code, most of it is just license headers and font for the display. So nearly half of it, around half of it, is the meat, like the code that can be analyzed. So that makes it really easy. Like 2,000 lines of code can be analyzed, let's say, within a week in details to make it, like, at least from the software perspective, bug free. And how the code looks like, I published this code a couple of months ago on GitLab. So on the first layer, there are basic drivers for basic communication peripherals and for calculations for signing Bitcoin operations, Bitcoin transactions. So I tried to, in order to keep the code base really low, I actually fixed the speed, communication speed for the UART bus and for SPI bus. So UART is I'm using really tiny implementation just to communicate with the communication microcontroller that then does all the, as I said, like all the heavy lifting that can communicate via even like Wi-Fi or Bluetooth or whatever to the rest of the world. And it's kind of like closing the possible space for like the attack surface for someone to remotely steal cryptocurrencies from hardware wallets. And the other part that is responsible for signing transactions is also mostly implemented in hardware, so code base is kept low. So there is this module, the LTC module, is responsible for cryptography operations, and MMCAU is used for calculating for the hash function, and I just get the nonce from true random number generator. And in case of the Cortex M0 version, I actually don't. It doesn't have the MMCAU, and it's the hashing is implemented in LTC. So the code base is even smaller in that case, and thus easier to analyze. And in LTC, I have these 5 basic operations that I use for signing these transactions. So they are basically modulo calculating the remainder, and modulo operations for inversion, for addition, for multiplication, and also for multiplying the point on the elliptic curve. And on the second layer, I just try to implement this really thin layer of like sending and receiving higher level packets that have like type, length, and data, and that are kind of like I do CRC just to be sure that to add some robustness on the bus, because it's really simple UART communication. And the OLED code just can write any row on the display or clear it, so it kept really simple without drawing any images or whatever. And crypto part is also offering these functionalities that one might need to sign Bitcoin transactions. Well, there is one operation that wasn't implemented in hardware completely, so I kind of had to, that's kind of the most complex part that I had to do by hand, was this. It was a division operation. So the way I implemented it was that I had, as I showed you, there is a modulo inverse operation and multiplicative inverse module operation. So then first I get I calculate that, then I deduct the remainder from the division of A with B, and then in order to get the result, I just multiply these two numbers. But in order for this to work, this number n has to be a really large prime number, because only in that case we can guarantee that for any A or B we can find multiplicative modulo inverse for, like, this is the first operation over there. In other cases we cannot guarantee that this number exists. So in order to find, I was thinking, like, okay, which number can it be? And then I thought, like, yeah, wait, I have 256-bit number that is prime and huge, that is P from the elliptic curve that is used for bitcoins. And on the final layer, in the main loop, I just receive the packet in a loop. It's a stupid state machine, so it doesn't have any interrupts, it doesn't have any handlers. It's just once it starts, it has multiple states that it can be in, like waiting for the packet and processing the packet and just or just calculating something. So it's waiting for some hardware peripheral to respond. So really simple operations. And after I receive a packet, of course, via UART, I transport it to some of the modules, depending on the type field in the message that I showed in the packet. And then in case it's for Bitcoin, I just direct it to the Bitcoin process function, and then there in that function I actually see what kind of operation I want to do, whether I want to initialize the transaction, whether I want to add some inputs or to add some outputs, or to actually ask the module to show the user that I want to sign the transaction. To show the user that he wants to sign the transaction. So this is how it looks like on the display once all the inputs and outputs are sent. So let's see how it looks in reality. I have a little device connected here, as a proof of concept, and let's see. So yeah, I don't know, maybe letters are too small, but so I can get the key pair from the device. So it's not meant to be used right away. Like, don't store your cryptocurrencies on this one. It's still, I don't trust it 100% because even with this function you can still read out the private key, and so, but this is just meant to be a proof of concept. So I can get my address that I have on this device, where I have some Bitcoin. So let's generate a new transaction, because Bitcoins were on sale recently. It was Black Friday sale, I guess. So now I send inputs and outputs to the device. I have a small prompt here. I don't know, like, I guess you cannot see it from there, but I'm just gonna confirm the transaction. Okay, and transaction is has been signed by the wallet, and I can choose here to submit the transaction. So transaction was submitted successfully. Let's see what it says. Okay, we see one unconfirmed transaction for this address that I used. So this is this proves that this wallet did in fact sign the transaction that I just sent to it. Give me a moment. Okay, so to continue. What's next? So next steps would be for this code, because it's open for everyone to use. It's open for everyone to actually to add functionality to it. So it's not a commercial project. One of the things that I wanted to add first was the U2F functionality. So that would require adding this on the communication controller some functionalities that are so that it complies with the CTAP protocol, which is one half of this FIDO2 project. So the other part is WebAuthn, that is used for communication between any of these online services and your computer or phone or whatever you use for accessing these services. Or as I said, there is this communication microcontroller that can talk all other by all other means, like not just USB, as I showed in this proof of concept. In case it's a microcontroller that also supports USB, NFC, or Bluetooth, you can also then use it for more in a more flexible manner, so you can use it with your phone or some other device. And there's also another version of these two microcontrollers, but that one requires an NDA to be signed with the manufacturer. But these are also like that they have some kind of tamper protection around the same core and all other peripherals that are used in this project. So if you want to make really safer and robust device, you might want to consider using one of these. And yeah, I also have plans to implement recovery seed for this, to implement actually these 3 Bitcoin implementation proposals, like BIP 32, 39, and 44, at some point. And yeah, of course, more cryptocurrencies. But as I said, this was just my side project. So feel free to send pull requests for this. It's on GitLab. You saw the link before. And yeah, I'm looking forward to your pull requests. Any questions? No questions? Okay. Thank you very much.